Welcome to this explainer. Today we are absolutely going to crack the code on AC generators, and I'm going to give you the exact step-by-step strategies you need to maximize your Cambridge physics exam marks. I want you to think of your physics exam, whether you're sitting for syllabus code 0625, 0651, 0652, 5054, or even 9702, exactly like a high-stakes Formula One race. You are literally racing against the clock, and every single mark counts. The AC generator questions, well, those are your critical pit stops. A smooth, highly systematic approach gets you back out on the track in first place. But a clumsy, disorganized, panicked answer, that's going to cost you the entire championship. So what we're doing today is taking elite pit crew strategies and applying them directly to your exam timing and your multi-stage physics analysis. We're going to look really closely at the simple form of the AC generator. We'll dissect the essential hardware, things like the rotating coil, the slip rings, and the carbon brushes. And we'll map out exactly, and I mean exactly, how the physical position of that coil dictates the peaks, the troughs, and the zeros on an electromotive force, or EMF, against time graph. Most importantly, I am going to show you precisely what the principal examiners are looking for when they have their red pens hovering over your exam paper. Let's get into it.
Okay, let's dive right into the most crucial question of the day. Why do so many incredibly smart students struggle with multi-stage analysis when the underlying physics is actually sitting right there in front of them? Well, let's consider the two typical students you're looking at right now. On the left side, we have Alex. Now, Alex works hard. Alex has memorized literally every single textbook definition. But when asked a complex question about an AC generator, Alex completely overloads the answer with raw physics facts. We're talking a massive, overwhelming paragraph of text that entirely forgets to provide any actual causal analysis, connecting the physical components to the electrical output. There's no link. Then, on the right side, we have Sam. Sam looks at the clock, feels the immense pressure of the ticking timer, rushes through the question, writes one brief panic sentence, and completely misses the specific command word requirements like explain or evaluate. Both Alex and Sam walk out of that exam hall feeling pretty confident. But when results day comes, both have lost massive easy method marks. The real tragedy here, guys, isn't a lack of knowledge. It's a lack of strategy.
So, to fix this, we are going to follow a highly structured approach today. We'll start with Section 1, the challenge of multi-stage analysis. Then, we'll hit the core concepts, move right into the standardized sequence for processing any problem, look at direct examiner warnings, and finally wrap up with the ultimate evaluation blueprint. Starting with Section 1, the challenge of method marks and multi-stage analysis. The absolutely crucial point you have to understand here is what examiners are actually doing. They frequently award marks for your analytical process, not just for stumbling into the isolated final answer. Let's look at exactly why students miss these critical, foundational steps. If you read the syllabus, it clearly, explicitly emphasizes that rote memorization simply isn't enough anymore. You have to demonstrate how fundamental physics principles integrate to solve complex, totally unfamiliar problems. This quote right here, this is the golden rule of Cambridge exams. Let's actually break down what connected conceptual understanding really means in practice. It means you don't just know what a slip ring is in isolation. You know exactly what would happen to the EMF output graph if that slip ring was suddenly ripped out and replaced by a split ring commutator. It means taking established principles of systematic analysis and evidence-based reasoning and applying them to a generator that might look slightly different from the diagram in your textbook. Top-performing students are basically code breakers. They decode the specific command words in the prompt. If the command word says describe, you just list the components and what they do. Easy. But if the prompt says explain how the output is generated, you absolutely must use a logical framework. Top students often use the Peel framework. That's point, evidence, explanation, link. They make a point about the coil's rotation, they provide evidence from the specific angle given, they explain the underlying physics of the magnetic flux cutting, and finally, they link it all back to the resulting EMF output. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, moving right along to Section 2, Core Concepts of Hardware and EMF Graphs. Let's see exactly how this theoretical architecture builds directly upon the precise definitions of generator components. Because, honestly, you cannot analyze a system without knowing the right terminology. Before you can even begin to analyze a system, you must be able to clearly, accurately define the physical roles of the slip rings and brushes. This right here is where so many students drop the ball. Picture a simple rotating AC generator. The coil is spinning continuously, right? Now, if you just hardwired that spinning coil directly to an external circuit, those wires would twist, tangle up, and snap within a fraction of a second. So enter the slip rings and carbon brushes. The slip rings are permanently fixed to the rotating coil and they rotate right along with it. The brushes, on the other hand, are stationary contacts. They just press gently against the spinning slip rings. Their distinct, specific role is to maintain a continuous, sliding electrical contact between that rotating coil and the external, stationary circuit entirely without tangling the wires. What's absolutely vital to remember here is that because each individual end of the coil is permanently connected to its own separate slip ring, the alternating current produced inside the coil is directly transferred to the external circuit as an alternating current. If you mess this up and confuse it with a split ring commutator, which reverses the connection every half turn to produce direct current, you are going to lose every single mark on the page. Precise definitions matter. And this table brilliantly illustrates the exact causal relationship you absolutely must memorize. It shows how the specific mechanical position of the rotating coil dictates the peaks, the troughs, and the zeros on an EMF against time graph. Imagine that rectangular coil rotating inside a uniform magnetic field. When the coil is perfectly horizontal, the sides of the coil are cutting directly across the magnetic field lines at a sharp 90-degree angle. That means they are slicing through the absolute maximum number of field lines per second. Therefore, the rate of cutting magnetic flux is at its peak, and boom, the induced EMF is at a maximum peak. Conversely, when that coil rotates 90 degrees to the vertical position, the sides of the coil are moving completely parallel to the magnetic field lines. For that brief instant in time, they are not cutting any field lines at all, zero. The rate of flux cutting is zero, so the induced EMF drops to exactly zero. As it continues rotating back to the horizontal position, but now flipped 180 degrees, it cuts the field lines in the exact opposite direction. This gives you a trough, a peak, but in the negative direction. It is this continuous mechanical cycle of horizontal peak, vertical zero, horizontal trough, vertical zero, that generates that classic sine wave graph of alternating current. If you can clearly map the mechanical position of the hardware directly to the data points on the graph, you have mastered the core concept. Okay, Section 3, standardized sequence for processing the problem. Now that we have our core conceptual knowledge locked down, we need a systematic, repeatable way to process these multi-stage questions without panicking when the clock is ticking. This 5-step standardized sequence is essentially your secret weapon. It's how you extract data, interpret relationships, and draw evidence-based conclusions without accidentally skipping vital steps. Let's do a live rewrite right now mentally, okay? Let's look back at Alex's messy, overwhelming answer from earlier. Step 1, identify key elements. We look at the prompt and identify that we are dealing with an AC generator, slip rings, and an alternating graph. Step 2, apply relevant principles. We pull Faraday's law of electromagnetic induction from our memory. Cutting magnetic flux induces an EMF. Step 3, execute analysis with clear working. Here is where the magic happens. We write our Peel paragraph. We state the point that the coil rotates. We provide evidence explaining it cuts field lines at specific angles. We explicitly explain that the slip rings maintain the connection, and we link the horizontal position directly to the peak EMF on the graph. Step 4, verify results. We check ourselves. Did we explain the whole 360-degree cycle? Yes. Step 5, present an appropriate format. We make sure we use the correct scientific terminology and provided clear annotations if a diagram was requested. By systematically following this exact sequence, Alex's red pen marks literally transform into green check marks. You go from a frustrating 1 out of 4 to a perfect, flawless 4 out of 4. Stop scrolling, subscribe to our YouTube channel Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Section 4, examiner warnings and pitfalls to avoid. We've talked extensively about what you should do, but now we need to run an interactive workshop on what absolutely not to do. Get ready, because I'm going to challenge you here. Year after year, the principal examiners repeatedly note these 3 critical errors. The biggest one, failing to adapt your theoretical knowledge to the specific context of the question. That alone costs students easy grade boundaries. I'm putting a 60-second timer on the clock in my mind right now. Let's do a data scan challenge together. Imagine you're looking at a complex physics data table showing an AC generator rotating at exactly twice the normal speed. What is the core trend you need to extract? Think about it. If you double the speed of rotation, you double the rate of flux cutting, which means the peak EMF doubles. So the peaks are twice as high. But wait, there's more. The time taken for one full rotation is also halved, which means the frequency doubles, so the waves are squished twice as close together. Many students completely miss that second part. Okay, next up, let's do a find the flaw challenge. Listen very carefully to this sample student paragraph. The simple generator uses a rotating magnet. As it spins, it creates a current which travels out through a split-ring commutator. Did you catch the massive flaw? The sentence losing all the marks is the mention of the split-ring commutator. The prompt's context is an AC generator, which relies on slip rings. Providing an answer not specific to the context given, mistake number 3 right here on our list, just cost you the entire 4-mark question.
This is straight from the Cambridge Principal Examiner Report. Never, ever assume the examiner knows what you mean or that they'll give you the benefit of the doubt. Clear definitions of terms like EMF or slip rings act as your foundation for the higher-order analytical marks. So let's do a 30-second speed writing challenge right now. If you have a piece of paper, jot down exactly how you would start a perfect Peel paragraph explaining EMF. Time starts now. Listen, you shouldn't just vaguely say it makes electricity. You need to define it with precision. Electromotive force, or EMF, is induced when the rotating coil continuously cuts the magnetic flux lines. Boom! That is your point. Your evidence is referencing the specific diagram provided in the paper. Your explanation is detailing how the slip rings function. Your link ties it all back to the alternating sinusoidal nature of the output graph. If you consistently define your core terms before diving into the complex analysis, you completely insulate your answer from ambiguity. The examiner sees immediately that you possess that connected conceptual understanding. Section 5, the evaluation blueprint. We're going to use a deconstruct, solve, evaluate method. Finally, let's wrap all of this theory and strategy into an ultimate foolproof problem-solving methodology that you can confidently carry into the exam hall. By deploying this precise deconstruct, solve, evaluate framework, you ensure that every comparative analysis you write highlights both similarities and differences, all backed by hard physical evidence. When you face an unfamiliar context, say a really tough 6-mark question evaluating the evidence quality of a brand new generator design, you start by identifying the limitations and assumptions explicitly made in the prompt. You deconstruct it. Then, you break the physics down into logical, sequential steps to solve it, just like we did with the coil positions. Finally, you evaluate. You step back and check for reasonableness. Does your answer actually make physical sense? For example, if your graph sketch shows a constant flatline EMF for a continuously rotating coil, your evaluation step should trigger a massive red flag in your brain. A rotating coil must have an alternating EMF. This 3-step process is your ultimate safety net against silly mistakes. Moving from a basic description to those elusive higher-order assessment objectives requires identifying limitations and using comparative connectives to show relative importance. Look, a basic description just lists things. It has a coil, a magnet, and slip rings. That might get you 1 mark. But a higher-order evaluation compares approaches. It might say, while a basic simple AC generator uses a rotating coil inside a fixed magnetic field, industrial generators often use a rotating magnet within fixed stationary coils because it completely eliminates the need for slip rings to carry massive, dangerous currents, thereby reducing wear, tear, and electrical arcing. Wow, that is exactly how you secure the absolute top marks. By contrasting the basic components with advanced alternatives, you prove a much deeper command of the physics involved. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acexams_IGCSE and click that bell. Don't let another exam pass you by. I really hope this explainer has transformed how you view AC generator questions, and I want to leave you with one final, provocative thought. Exactly how will you apply this systematic sequence to your very next past paper practice? Are you going to continue to race without a pit crew, hoping for the best? Or will you use the deconstruct, solve, evaluate blueprint to absolutely guarantee your success? The choice, and ultimately the grade on that paper, is entirely up to you. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.